শুনতে পাচ্ছ তোমরা?
Yes, sir.
Okay. So perhaps this equation, our equation I have already discussed. P plus JQ, this is the active and reactive power. That means the complex power delivered by the machine. The development of this synchronous equivalent circuit was discussed based upon this phasor diagram. We have developed this equivalent circuit where this is the generated voltage, means the induced voltage. Induced voltage is making an angle delta with respect to the terminal voltage. Terminal voltage is the voltage of the infinite bus because the generator is connected to power system, which is considered to be an infinite bus, means constant voltage bus. Okay, and that bus is taken as reference. Now power flows from leading to lagging angle. Delta is EF at an angle delta. So delta is the phase angle at which the induced voltage is leading the terminal voltage, and the current delivered by the generator is given by this expression EF at an angle of delta, this voltage minus this voltage by Jxs. So complex power equation is Vi conjugate. V at an angle of 0, terminal voltage, Vt is 0, and I conjugate. This is I conjugate of this is taken here, and the real part is P is EF Vt by Xs sine delta, and reactive part is the imaginary part here. U is Vt by Xs EF cosine delta minus Vt. Now, how to control the active and reactive power that we were discussing in our last class. And if the field is kept constant, assuming that the field current is not changed, then obviously, since the generator is rotating at synchronous speed, so what will happen? Rate of change of flux linkage is constant, means EF is constant, and Vt is the infinite bus voltage, which is also constant. Xs is the synchronous reactance, also constant. So P is P maximum sine delta. That means for varying P, you have to vary delta. And what is the delta? Delta is the angle between induced voltage and terminal voltage. Now the question is how delta may be varied. You see that also perhaps we have discussed, because delta is this angle and EF is aligning with the quadrature axis of the rotor. That means if you can change the position of the rotor with respect to the terminal voltage, then delta will be varied. Okay, because EF is along the quadrature axis. Generator rotor is rotating at synchronous speed. Terminal voltage Vt, infinite bus voltage, is frequency is synchronous, means angular frequency of rotation is synchronous, and the angular speed or frequency of this rotor also is synchronous. That means this delta, the angle between the induced voltage and terminal voltage, this is constant. And at steady state, when the generator is working at stable condition, when the generator is rotating at synchronous speed, then delta is fixed. That means generator will be delivering a power, this power P, generator will be delivering a power P which is constant. This is how generator will be delivering a stable power to the power system. Okay. Now react, and therefore if you want to change the value of delta, that means if you want to change the value of P, then delta has to be varied. How delta may be varied? You see, this is the leading direction delta. So if you can increase the value of delta, then P will be increased. How to increase the value of delta? This Vt is rotating at synchronous speed. EF also is rotating at synchronous speed. So if you can rotate EF, that means if you can rotate generator at a speed higher than synchronous, then obviously with respect to this factor, EF will be rotating at a faster speed. As a result, delta will vary. So obviously, for this, what you have to do? You have to accelerate the generator. That means you have to increase the opening of the steam valve. Why we are talking about steam valve? Because we are talking about the cylindrical rotor generator. Cylindrical rotor machines are used in thermal power stations, and in thermal power stations we have the steam turbine. So opening of steam valve has to be increased a bit. Okay, if the opening of steam valve is increased, more steam will enter into the turbine. That means the steam flow rate will increase. As more steam flow is there in the turbine, turbine torque will increase, input torque will increase rather, and the output torque, that is constant. Why output torque is constant? Because you see that unless delta can change, power output cannot change. That means that there is a difference created between the T input and T output. Torque input, mechanical torque input and electrical torque output. There is a difference between these two. So machine will accelerate. Machine will rotate at a speed higher than synchronous. Obviously, that speed will not be very high than very large than synchronous. It will not be very differing by a large, you can say by a large quantity from synchronous. It will be moving slightly greater than synchronous speed. Otherwise, there will be a problem of maintaining the stability of the generator. So, generator will try to rotate at a speed higher than synchronous. As a result, delta will increase. As delta is increasing, you see from this power angle curve, as delta is increasing, obviously power output will increase. If the power output increase, what will happen? Difference between the input power and output power will get reduced. Means again the speed will be somewhat slower than the previous speed. In this way, generator is will rotate at a speed higher than synchronous, then power output will increase. As power output is increasing, then the acceleration will be reducing somewhat. In this way, what will happen? As power output increases, power output will become at some time, because the speed is increasing and acceleration is there, power output will become somewhat higher than the power input. So if the power output is more than power input, what will happen? Generator will decelerate now. It will decelerate from the speed at which it has reached, and that speed is above synchronous. So from the synchronous speed will again decrease. It will become synchronous, and then it will become less than synchronous. In this way, there will be oscillation of the rotor speed, and finally, when the generator again gets synchronous speed, it will be delivering more power than it was delivering previously, because by this time there was an increase in the opening of the steam valve. So, say previously generator was, this was the power input, and now say power input increases, it is somewhat here. If it is here, then what will happen? Generator will oscillate around this new position of P, and finally it will be stable here. If you want to increase the power output more, then again increase the opening of the steam valve. Again P will be increasing, it will be somewhere here. Generator speed will increase, it will become more than synchronous. Then again it will oscillate around this point. In this way, if you can increase the power input to the generator, that means if you can increase the steam flow rate by a very small amount, you will be in a position to reach up to this point, because this is the maximum power output position of the generator. That means if you can increase the opening of the steam valve in such a way that oscillation is there, but that oscillation is very small. Okay, initially at this part, when the generator was operating at this point, obviously it can withstand larger oscillation, no problem. But as it will be approaching this point, the peak point, then its ability to withstand oscillation will get reduced. Okay, so you have to increase the input very slowly, and if you can increase the input very slowly, you can reach at this point. Okay, so this is the maximum power output position of the machine. Now assume that you are operating or the generator is operating at this point delta equal to 90 degree. And we want to say somehow we have increased the power input to the generator by opening the steam position of the steam valve further. Say it is made somewhere here. Input is somewhat more than the power output, which is the maximum power output. Now what will happen? If the input is more than this point, then obviously the machine speed will increase further. But now note the difference. If the input is increased above this point, that means if the speed is exceeding synchronous, then delta will increase. As delta will increase, power output now decreases. It is not increasing any further. Up to this point, with the increase in speed, delta was increasing. With the increasing delta, output was increasing, and the machine could regain the synchronous speed again. It was initially above synchronous, but then it became synchronous again. But if the operating point is this one, and then if the power input increases, then delta will increase because of the increase in the speed of the generator, but generator will not be able to increase its power output. That means difference between input and output will increase. As a result, speed will increase further, and this will lead to a position where, to a situation from where generator will not be possible to regain its synchronous speed again, because as power output is decreasing, difference between input and output increase will get increased continuously. So as a result, generator will become unstable. It will not be able to regain synchronous speed. It will not be able to restore the synchronism again. Thus, this point from 90 degree to above value of higher value of delta, this may be identified as the unstable operating zone of the generator. And from delta equal to 0 to this point, delta 90 degree for cylindrical rotor machine, we can say that here the machine will be, or the generator will be operating at stable condition. Why at stable condition? Because as we are attempting to increase the power output, generator power output is increasing. But here, if you want to increase the power output will get reduced. Any attempt to increase the power output will rather reduce the output of the generator. That means for delta greater than 90 degree, the operation of the generator will be unstable. And from delta 0 to 90 degree, obviously this is the stable operating zone. So when the machine is operating at steady state, its operating angle has to be from 0 to 90 degree. During the oscillation, it may be such that sometimes delta may cross 90 degree, but it will be coming back to a value which is below 90 degree, because at stable condition the operating angle has to be below 90 degree. Okay, that's why this area we actually we may identify as the unstable operating zone of the generator, and from here to here it is a stable operation zone. Okay, so is it clear to you that for varying the active power output, it is the active power input to the generator through opening of the steam valve for cylindrical rotor machine and through opening of the water valve for hydroelectric generator, that has to be controlled. Okay, any question here, any doubt here? বলো, কারো কোনো কোশ্চেন আছে? If there is no question, then reactive power variation, how the reactive power may be varied. We are assuming that we shall be keeping active power output constant. That means we shall not be changing the steam input to the generator, it will be remain fixed. Obviously active power is the working power, so unless you give any additional active power input, you cannot increase the active power output. So obviously the active power output will remain constant, so this is remaining constant. That means active power output is remaining constant means if we talk in terms of P max and delta, then P sine delta, that means P maximum sine delta will remain constant. According to this expression, you see that you have to keep P max sine delta constant. Alright. So, or EF sine delta has to be kept constant. Same thing because Vt is constant. So, EF sine delta has to be kept constant, but EF cosine delta may vary. Alright, EF sine delta, our control will be such that EF sine delta will be constant. So assume that this is the line showing the which is parallel to this line Vt. Okay, that means this length EF sine delta, EF sine delta, EF sine delta will remain constant, and we have drawn three value of EF here: EF1, EF2, and EF3. EF1 is the induced EMF corresponding to a certain value of field current when the armature current is like this IF1, because if this is EF1, this is Vt, this perpendicular vector, it will be JIA excess, that means J into armature current into excess. Here it is IF1, but actually it should be IA1. So JIA1 excess is this length. Then it is EF2. The length of EF2 is somewhat higher than EF1. How this may be higher? Obviously, rate of change of flux linkage has to be made higher. And speed is constant because it is a synchronous generator. So what has to be changed? By changing the field current. So somehow you have changed the field current. Field current at EF2 is greater than the field current at EF1. Okay. So this field current corresponding to this EF2 is greater than field current corresponding to EF1. Obviously by mistake of the drawing, it is IA3, it is IA1, it is IA2, not IF2, IF1 and IF3. Okay, but field currents corresponding to this EF2 is greater than the field current corresponding to this EF1. That's why EF2 is greater than EF1. Now note that we have kept EF sine delta constant, that means this length and this length, these are constant, but EF cosine delta, this is the length, this EF2 cosine delta, this is the length. So EF2 cosine delta is greater than cosine delta 2 rather is greater than EF1 cosine delta 1. Okay. Now what happens when EF2 is greater than EF1? You see that this delta 2 is smaller than delta 1. Now if you reduce the value of field current, say field current is such that it is smaller than the field current corresponding to EF1. So then EF3 becomes smaller than EF1, and at this condition delta 3 is larger than delta 1. That means if you increase the field current, delta value will decrease. If you decrease the field current, then delta value will increase. Okay, and what is the result of this change of delta? This change of delta ultimately make EF cosine delta value to vary. So if OF cosine delta varies, if it is greater than Vt, in that case Q will become positive. If by varying the field current again we make EF cosine delta less than Vt, then it will be negative. And also it is possible to make EF cosine delta equal to Vt. In that case Q will become 0. That means reactive power, you see, it may be changed by, or it may be varied by varying the value of field current. And when EF cosine delta is equal to Vt, then what happens? Q becomes 0. If Q becomes 0 means generator is delivering active power and neither delivering nor consuming reactive power. That is, a purely active power is being delivered by the generator. That means the power factor of the generator is unity. So this is corresponding to this position. EF1 and IF1 is the IA1 rather it is the armature current. Okay. So in that case, VT and IF1 or VT and IA1 rather, they are in same phase. That means the power factor is unity. This particular operating condition, that is the field current corresponding to this operating condition, is known as the normal excitation condition or normal excitation of the generator. When field current is increased than this value, then maybe situation is like this. In that case, you see that IF armature current will be lagging this by 90 degrees. That means this will be the position of the armature current. And in that case, generator current is lagging the terminal voltage, means it is the lagging power factor condition. Field current is higher than the normal current. This is the overexcited condition of the generator. And if you reduce the field current, then what happens? You see that in that case, delta increases, this becomes a vector JIA3 XS, and this becomes the vector IA3. So this armature current is now leading the terminal voltage. That means the generator is now operating at leading power. So generator is under excited means generator is operating at leading power factor. Generator is over excited means generator is operating at lagging power factor. And when EF cosine delta becomes equal to VT, then generator is operating at unity power factor. Field current corresponding to this consuming any reactive power. The generator operating power factor is unity. So when the excitation is normal, this operating condition is called the normal excitation condition. Okay. Here, the generator power factor is unity. And when the excitation or when the field current is greater than this value, then it is overexcited. When the field current is less than this value, then it is underexcited. So, underexcited synchronous generator, you see that here Q is negative because EF cosine delta is less than VT. Q is negative means if positive Q represents the power delivered, then negative Q certainly represents the power consumed. That means generator is consuming reactive power. No doubt it is delivering active power, but it is consuming reactive power. So note that overexcited synchronous generator will be delivering reactive power. Normally excited synchronous generator will neither deliver nor consume reactive power, and under-excited synchronous generator will be consuming reactive power. Alright, any question here? Anybody? Any question? Now the question is, what is the limit of under-excitation? You can reduce the field current, but how long you can reduce it? How far it is you can reduce it? Okay, obviously you see that if we refer to this Phasor diagram, what was the limiting value of delta? It was 90 degree for cylindrical rotation. And if you reduce the field current, delta value actually increases. So obviously, if delta value is increasing, how far you can allow delta to increase? Obviously, from this diagram, power angle diagram, and from this explanation we have already made, you see that delta value may be allowed to increase up to 90 degree for cylindrical rotor machine. That means this is the condition up to which we can allow the generator excitation to be reduced. That means reduction in the field current may be allowed up to this point when delta reaches 90 degree. So this particular operating condition represents the minimum excitation limit of the generator, and minimum excitation limit obviously is represented by, or it is controlled, or it is decided by the stability of the generator, steady state stability of the generator, because at steady state stability delta value is equal to 90 degree for cylindrical rotor machine, and we are discussing now the cylindrical rotor machine. Here excitation may be reduced up to that point when delta value reaches 90 degree for cylindrical rotor machine. So minimum field current condition or the under excitation limit will be decided by the stability of the generator. Now the question is, if you overexcite the machine, that means if you supply larger field current than normal excitation condition, what will be the maximum field current that you can deliver? Who will decide that? What will be the deciding factor? Or what will be the limiting factor? As in this case, the minimum field current is actually decided by the stability consideration. What will decide the maximum field current? Any guess, anybody? Who will decide how much reactive power generator can deliver, or how much we can increase the field current of the generator, because that will decide the reactive power that the generator may deliver. If you increase the field current, there will be increase in the I square R loss in the rotor circuit, in the field circuit, means there will be heating of the rotor, and rotor heating therefore will decide the maximum value of field current, or over excitation limit will be decided by the generator rotor heating, under excitation limit will be decided by the stability of the generator. All right, ঠিক আছে, বুঝতে পেরেছো? Any question, anybody? Now for that was regarding the cylindrical rotor machine, cylindrical rotor synchronous generator. Now it is it is we shall be discussing about the something regarding the synchronous motor also, because we shall be discussing the frequency control and voltage control. You see that synchronous generator basically is a generator where the field current is DC and armature obviously is AC. In synchronous motor also, field current is DC, and the operating principle of synchronous generator and motor there obviously will be same. Okay, there will be field current delivered from DC, and there will be armature which is AC. In case of synchronous motor, motor will receive power from the power system. That's why the direction of power flow is just reverse. Okay, but the field current, obviously, you can over excite, you can under excite, or you can give normal excitation to the synchronous machine motor. Here also, what we have done in case of generator, the same thing may be done in case of motor also. Okay, so what will be the phasor diagram for motor? You see that, as you have already mentioned, in case of power flow, when the we have derived the phasor diagram of generator, and from where we have actually derived this equivalent circuit from here. Power actually flows from leading vector to lagging vector. For generator delivers power to the power system. So power flows from machine to the system. EF is leading VT because power flows from EF to VT. In case of motor, what happens? Especially in case of motor, there also will be an induced EMF. There also will be power flow, but power will flow from our system to the motor. Okay, power system to the motor means this is the system voltage, this is the motor generated voltage, and since direction of power flow is from bus bar to machine, this VT will lead EF. Okay, VT will lead EF because power is flowing from terminal voltage to induced EMF. Here note that the magnitude of EF may become greater than VT, and then also power is flowing from terminal to induced EMF. Okay, so the power flow, it depends upon the phase relation, not on the magnitude of voltage in case of AC. From leading vector to lagging vector, power will be flowing. Okay, so now let us discuss the situation when the generator is overexcited. That means when EF cosine delta is greater than VT, as we have discussed in case of motor generator also. EF cosine delta is greater than VT means field current is above normal field current. Normal field current corresponds to that operating condition when EF cosine delta is greater than is equal to VT, because then the power factor becomes unity, then Q becomes 0. In this case, EF cosine delta is greater than VT. Okay, so EF cosine delta, when it is greater than VT, obviously the motor, it will follow the same this expression for active and reactive power. Okay, when the Q is positive, obviously the machine will be delivering power to the machine will be delivering power. That means the synchronous motor will be delivering reactive power to the bus bar. It will be drawing active power, but reactive power it will be delivering. So this particular operating scenario, when the motor is drawing active power but delivering reactive power, so this is called the operation as synchronous condenser, because the generator, this motor is behaving like a capacitor. Why it is behaving like a capacitor? Because a capacitor delivers reactive power. Here the motor also, which is otherwise a load, consuming active power, but in respect of reactive power, it is behaving like a generator, it is behaving like a condenser, it is behaving like a capacitor. Since capacitor are also called condenser, this particular operation, that means the overexcited operation of the generator, is called the operation as synchronous condenser. Not only overexcited condition, when the generator is running at no load, sorry, motor is running at no load, because the whole purpose of running this motor now is to actually inject reactive power to the system. Motor will be receiving some power, and that power is the nominal power. That means motor will be taking active power to supply its losses only, but it will not be actually driving any load. It will not be delivering any mechanical power to some load. Okay, so that's why motor will be operating at no load, but its field current will be kept above normal so that it can deliver reactive power to the machine, to the power system. And what is the purpose of delivering this reactive power? Because by delivering reactive power, the motor will take part in voltage control, because we know that reactive power and voltage, these two are closely coupled, these two are strongly coupled, and for controlling the voltage, it is the reactive power flow that has to be controlled. So synchronous motor therefore may be utilized for voltage control purpose. Already we have mentioned that active power control is possible only from power station because we need generator. But reactive power control is possible from anywhere, almost from anywhere. From power stations, that means the generator can control reactive power, generator can control voltage. You can install a shunt capacitor, sorry, synchronous motor anywhere. So if a synchronous motor is installed, that can delivering reactive power, so that can also participate in voltage control. Okay, and synchronous condenser. This particular operation of the motor is called the operation of synchronous condenser, and which is basically an overexcited synchronous motor running at no load. Why running at no load? Because our purpose is not to drive any mechanical load. Our purpose is to utilize the motor as a controller of reactive power. That's why it is running at no load condition, and this time the motor is used for voltage control purpose. Okay. Now this was regarding the synchronous generator, cylindrical rotor synchronous generator. Already we have mentioned that initially we shall assume that our machine, our generator is cylindrical rotor, but then we shall actually discuss about the Salient pole generator as well. So let us now discuss regarding the Salient pole generator. What is a Salient pole generator or what is a Salient pole machine? Salient poles mean projected pole. You can actually see the poles from outside. If you look at the rotor, you can identify these are the position of the rotor because poles are projected. So there is an air gap between the rotor and the stator. In case of cylindrical rotor machine, this air gap is constant because poles are not projected. Okay, everywhere around the periphery of the generator rotor, gap is uniform. That means if you measure the reluctance of the magnetic circuit, the reluctance is uniform. Means you have same reactance measured from anywhere. That's why cylindrical rotor machine may be represented by single reactance. In case of Salient pole machine, the air gap is not uniform. Along the pole axis, it is minimum. If you go move away from the pole axis, okay, that is between the two poles, just between the two poles, it is the maximum. So reluctances also are not uniform. Along the pole axis, it is minimum air gap. Along the quadrature axis, it is the maximum. That's why two reactances will be necessary. Two reluctances are there. One along the axis of the rotor, direct axis of the rotor, and or pole axis, another along the quadrature axis. So Salient pole machines may be represented by two reactances. One is called the direct axis reactance, and that is called the quadrature axis reactance. This particular representation of the Salient pole machine is called known as the two reaction theory. That means there is armature reaction and there are two armature reaction. These reactions are different. Along the pole axis, if you see the armature reaction, the reaction is different from the reaction that happens in case of the quadrature axis position. Okay, that's why Salient pole machines are represented by two reactances. One is direct axis reactance, another is the quadrature axis reactance. So with this, let us discuss the phasor diagram of the Salient pole machine. Say this is the direct axis D, written D, it is the direct axis, and 90 degree with this is the quadrature axis. Say this is the terminal voltage, and this I is representing the armature current. So what we shall do to represent the armature reaction, we shall be actually divide the or take the projection of the armature current on the quadrature axis as IQ and on the direct axis as ID. So ID is the direct axis component of armature current. IQ is the quadrature axis component of the armature current. That means if you want to show the armature reaction, which will be shown here in terms of voltage drop, reactance multiplied by current. So armature axis, quadrature axis armature reaction will be represented by JIQX XQ. XQ is the reactance along the quadrature axis, and direct axis component of armature reaction, that will be represented by JID XD. XD is the reactance along the direct axis. Okay, so this is V, terminal voltage, plus JID JID, it is 90 degree with ID, that's why JID XD, it is the drop along the direct axis. Then JIQ XQ, that means drop along the quadrature axis. Okay, due to quadrature axis reactance, JIQ is the voltage drop. This JIQ is 90 degree with IQ. So E is written as here, you see, V plus JIDXD plus JIQXQ. Okay, E equal to V plus JIDXD plus JIQXQ. All right. Now, also we can write this equation, E minus IDXD. We are checking only the magnitude, only this length. Say E minus this length. What is this length? This length is nothing but the product of IDXD. So E minus IDXD, obviously this is equal to VQ. VQ means V cosine delta. So V cosine delta is E minus IDXD. From here you can find out the value of ID equal to E minus V cosine delta by XD. Similarly, you can say that it is V sine delta, it is VD. This length is equal to this length. So V sine delta, this is equal to IQXQ. Okay, means IQXQ equal to V sine delta. So get the value of IQ from here. Now let this angle is beta, that means the angle between the induced EMF and the armature current. What you can say, this beta is the summation of delta and phi. Phi is the power factor angle between I and V, and delta is the power angle or load angle between E and V. So you can say that I cosine beta, this is equal to IQ, I sine beta, this is equal to ID. All right. And power factor phi, that is beta minus delta. So we shall be finding the expression for active power and reactive power. Active power is VI cosine phi. So to find out that, let us find out the value of cosine phi. Cosine phi means cosine beta minus delta. Okay, beta minus delta. It's delta actually, not phi. Beta minus delta. So cosine delta plus sine beta sine delta. Similarly, to find out the reactive power, we have to write VI sine phi. So find out the value of sine phi. So sine of beta minus delta. So sine A minus B, sine A cos B minus cos A sine B, sine beta cosine delta minus cosine beta sine delta. Okay. So I cos phi, you find the value. I sine phi, you find the value. So I cos phi becomes IQ cosine delta plus ID sine delta. I sine phi becomes ID cosine delta minus IQ sine delta. So find out the value of VI cosine phi. If you put the values, you will be getting these values. EV by XD sine delta plus B square by 2, 1 upon XQ minus 1 upon XD sine 2 delta. So this is the expression for active power. VI cosine phi is the active power, and the value is EF by XD sine delta plus B square by 2, 1 upon XQ minus 1 upon XD sine 2 delta. So active power expression is EV by XD sine delta plus this portion. You see that this first part, sine delta part, is almost identical with that cylindrical rotor type machine where it was EV by XS sine delta. Here it is XD there it was excess. Obviously, for cylindrical rotor machine, there is no difference between excess and between xd and xq. Everything is excess. So this portion you can say this is the expression for active power for cylindrical rotor machine. But for salient pole machine, another component exists. Why this another component exists? This is existing because of the difference between xq and xg, or because of the difference between the air gap along the two positions of the uh, along quadrature axis and direct axis. So this is because of the difference between the reluctances. That's why this part is called the reluctance power. Reluctance power. V square by 2, 1 upon xq minus 1 upon xd, sine 2 delta. The sine 2 delta component is solely due to the difference between xq and xd. Had xq and xd were same, that means in case of cylindrical rotor machine, you see that both are excess, so it becomes 0. So sine 2 delta component vanishes if the air gap becomes uniform. Since air gap is not uniform, there are differences in reluctances along the two axes. That's why this component v square by 2, 1 upon xq minus 1 upon xd sine 2 delta, this is appearing, and this particular this component is called the reluctance power. What will be the value of this reluctance power? It depends upon the value of xq and xd, and maybe 15-20% of the total. Okay. So now if you draw the power angle curve for salient pole machine, you will have a sine delta component, and along with that there will be a sine 2 delta component. Means sine delta component is obviously like this. What will be sine 2 delta component? It will be the half cycle completed here, the negative cycle here. So if you get the resultant, you see that here the resultant power angle curve value will somewhat higher. It will be maximum at somewhere uh, here before the value of delta equal to 90 degree, and then it will be at delta equal to 90 degree, it will be here, and then it will be getting reduced here. So the stable portion here, the amplitude will be somewhat higher, peak will be somewhat somewhere ahead of delta equal to 90 degree, and after delta equal to 90 degree, it will be less than the sine value amplitude of the sine delta curve value. Okay, that means during the unstable part, its value will be getting reduced. Throughout the stable part, its value will be somewhat higher. Or we can say that for salient pole machine, what will happen? Because of the presence of the sine 2 delta component, since the amplitude will be somewhat higher, for small change in delta, there will be a larger change in the value of power. Okay? That means if you want to increase the power, a smaller variation in delta is necessary. Or you can say that stiffness of this machine, stiffness means how strongly the machine is coupled with the system. System means system voltage, VT, and machine is represented by its induced EMF. So how strongly EF and VT, or E and V, they are coupled. They are really strongly coupled. Why strongly coupled? Because you require more power to create a variation in the value of delta. In that sense, stiffness of salient pole machine is higher than the stiffness of the cylindrical rotor machine, we can say. But there is another difference. What is the difference? The spread of the stable operating zone, it is somewhat less here, because the peak of the power angle curve will be reached before somewhere before delta equal to 90 degree. You cannot go up to delta equal to 90 degree because of the sine 2 delta component. What is the value of sine 2 delta component? It is around 15 to 20% of the sine delta component. Okay. So you can say that the zone of stable operation is getting reduced, but stiffness of the machine is becoming higher. Stiffness of the machine is becoming higher means the machine is more tightly coupled with the system voltage, means inherent stability of Salient pool machine is somewhat higher than the cylindrical rotor machine, but the expand of the stable zone is somewhat reduced. Okay, you cannot reach uh, delta equal to 90 degree during stable operating condition. It will be somewhat less. So otherwise the control is same. For varying delta, you have to change the input power to the turbine, and for frequency control, obviously active power has to be changed. What about reactive power? If you draw the expression, find out the expression Vi sin pi, you see that it is also very much similar. Had xd and xq been same, so it would have been v square by xs only, because cosine square delta plus sine square delta would have been equal to 1. Okay, so EF Vt by xs, EF cosine delta minus Vt would have been the expression. So again, this component here is coming because of the difference in reluctance at the two axes of the generator. Okay, so here also voltage control, same logic will be there. You have to control the value of E. You have to change the field current of the generator to change the reactive power generated. Okay, so you see that the means a mechanism of control of active and reactive power in synchronous generator. This is similar in case, this is same rather, in case of cylindrical rotor machine and salient pole machine. Active power control, for active power control, delta has to be controlled. For controlling delta, you have to control the input power to the turbine, and control the, for control of reactive power or for control of voltage, you have to control the field current of the machine, field current of the generator. Okay, so we have discussed the salient pole generator, how that may be controlled. It is very similar to the cylindrical rotor machine. Also, we have discussed about the synchronous motors. We have seen that synchronous motors may be operated at a no load condition under overexcited situation, and if the motor is overexcited, then it can deliver reactive power. One thing on difference between the motor and generator you have to note. For synchronous motor, overexcited operation gives you lagging power factor. Okay, uh, overexcited condition gives you the leading power factor, and for synchronous generator, overexcited condition give you the lagging power factor. So overexcited synchronous generator will operate at lagging power factor, but overexcited synchronous motor will operate at leading power factor. Overexcited synchronous motor is very similar to, in operation, it is very similar to the capacitor. That's why it is called the synchronous condenser. Okay. Now, after these discussions in the PPT that I have already mailed to you, we have two problems discussed. One is this one, which is also solved here. I shall be explaining this, and another is this one. Solution is not given. I shall be explaining the solution today. Okay. Now you see what is the problem written. A turbo generator. Turbo generator means basically the generator connected at steam turbine, are also called turbo generators. Generator driven by steam turbines are turbo generator. Turbo generators feeds 0.25 per unit power. You are familiar with per unit representation. You know that for power system calculation, for power system analysis, per unit system is very, very useful. Why? Because due to the presence of transformer, there will be change in the voltage level, and as the voltage level changes, current also will change, impedance also will change. This creates difficulty in continuing calculations in power system because there will be so many voltage levels in power systems. To avoid that, per unit system has to be used, and for per unit system, what has to be done? You have to select a voltage base at a location and a power base throughout the system. For a component, when we express in per unit, then the rating of the component is considered to be the base value. That means the rated voltage of the generator will be the base voltage, rated power of the generator will be the base power. Okay. But when we consider a large number of generators or large number of machines, large number of components, then we have to convert all impedances or all values with respect to a common base. Common base means voltage base as a particular location, and voltage base will change according to the change in location. That means into with the presence of transformer, obviously voltage level will change and voltage base also will change. But power base will remain same everywhere because power is same at the primary and also at the secondary of the transformer. So power base will remain same, but voltage base will change. So here the turbo generator feeds 0.25 per unit power. That means 25% of its rated capacity. Because here the 1 per unit power means the rated power of the generator. To infinite bus. Generator is connected to infinite bus, this is connected to infinite bus, and it is delivering 0.25 per unit power. Infinite bus voltage is 1 per unit, means infinite bus voltage is the rated voltage is considered to be 1 per unit in the base bus. The excitation voltage is 1.5 per unit. That means EF. EF is 1.5 times the terminal voltage, 1.5 per unit, and the synchronous reactance is 1 per unit. Reactance, what is the base value of reactance? Base voltage by base current is the base reactance. So with respect to that, 1 per unit is the base synchronous reactance. You have to calculate the load angle. Load angle means power angle, delta, and the reactive power output of the generator. Active power output is given, it is 0.25 per unit. You have to calculate the reactive power. So you have to calculate the value of delta. You know the value of E, you know the value of V. Xs is given. So you calculate delta, you can calculate EF cosine delta minus Vt. Very simple. Now calculate the changes in the active and reactive power outputs if two conditions are given. Number one condition is the turbine valve opening is increased corresponding to 100% increase in the turbine torque. Turbine valve opening is increased means active power is being controlled. How? By increasing the opening of the valve by 100%, because 100% means previous opening was considered at 100%. Now there is an increase in 100%, means the active power input becomes double of the previous value. Previously it was 0.25 per unit power because this was the power delivered. We shall be neglecting any losses in the generator. That means power input was also 0.25 per unit. Now steam valve opening is increased by 100%, means power output will become 0.5, power input becomes 0.5 because the opening has increased. Okay, keeping the excitation constant. So field current is not changed. So let us solve this part first. So what is the question given? Generator is delivering 0.25 per unit power. Terminal voltage is 1 per unit. Generated voltage is 1.5 per unit. Reactance is 1 per unit. And under this condition, you calculate the value of reactive power by calculating the value of delta and calculate the you have the turbine valve opening is increased. Okay, keeping the excitation constant. Okay, so and there is second control. So under this condition, you have to calculate the change in active and reactive power. Okay, so first part, you give that Vf is given, Vt is given, EF is given, P is given, XS is given. So you can use this expression P equal to EF Vt by XS sine delta. From here you can calculate the value of sine delta and delta, which is 9.6 degree. So if delta is 9.6 degree, you can calculate reactive power EF Vt by XS cosine delta minus V square by XS. Okay, which becomes equal to 0.48 per unit. That means when the generator is delivering 0.25 per unit power, active power, it is delivering 0.48 per unit reactive power. Now what is done? Torque control is done. 100% increase in the valve opening. So obviously 100% will be the increase in power. So active power becomes zero point 0.5 per unit. So if it is zero point 0.5, what is the value of sine delta? Because power input is increasing means obviously delta will increase. Delta becomes 19.5 degree from this calculation. If delta is 19.5 degree, what becomes the reactive power? EF Vt by XS, because EF is kept constant. Simply delta is changing, cosine delta minus V square by XS, it becomes 0.41 per unit. That means when the active power is increased by 100%, there is somewhat reduction in reactive power. It becomes 0.41 per unit from 0.48 per unit. How much is the reduction in reactive power? QZ decreases by 15%. You see that 100% increase in active power results in 15% reduction in reactive power. So we have previously discussed regarding system that active power and delta, they are strongly coupled. Reactive power and delta, they are weakly coupled. You see that here delta is increased, and as delta is increased, active power is increasing. Very large increase in active power, 100%. But what is the reduction in reactive power? Only 15%. So here also, there the same fact is established again that delta and reactive power, they are very weakly coupled. And delta and active power, the coupling is strong. Okay. Then the next part, what was the next part? The question was keeping the turbine valve opening fixed at the initial value. Initial value means corresponding to 0.25 per unit power. The excitation is increased by 100, increased, it should not be by, it will be 2. The excitation is increased to 120%. So 20% increase in excitation means field current. That means if the field current is increased by 20%, obviously it will become 1.8 per unit from 1.5 per unit. Because 1.2 times 1.5 means 1.8 per unit. But no change in active power output. It is same as the initial value 0.25 per unit. So 0.25 is the power. You put the value of EF to be 1.8, find out the value of delta, which is 8 degree. Previously it was 9.6 degree Celsius. Now change in field current change the value of delta, but by a small amount, from 9.6 to 8 degree. How much is the change in QG? It is EF Vt by XS cosine delta minus Vt is 0.78. You see that from 48, from 0.48 it became 0.78. So there is a large change in reactive power. How much? For 20% change in field current, there is 63% change in reactive power. So again you see the coupling between voltage and reactive power. Voltage means induced voltage and reactive power. Coupling is rather strong. 20% increase in voltage, excitation voltage, resulted in 63% increase in the reactive power. So again, like the power system, like the network, in case of machine also you can see that reactive power and voltage, they are very strongly coupled. So from this example, that is re-established. The decoupling principle that we say in case of power system, it is re-established here that active power and delta, they are very strongly coupled. Active power and uh, voltage, they are very weakly coupled. Voltage and active reactive power, they are very strongly coupled. And coupling between voltage and active power, that is rather weak, because in this case, the second case, voltage has been changed but there is no change in the active power. Why there is no change in the active power? Because you are keeping steam input constant. Unless there is an additional input power given to the machine, how can it deliver more power? Because active power cannot be generated from anywhere, it can be converted again. Okay, since there was no supply of active power, there is no supply of additional active power, there is no additional output of active power as well. All right. Now, perhaps this is clear to you, or if there is any doubt, you may ask me questions. Now, this example, which is not solved here, I shall be explaining this. A 13.8 kV 100 MVA 50 Hz synchronous generator delivers a load of 75 MVA at zero point 0.9 power factor lagging to an infinite bus held at 1 per unit. That means infinite bus voltage is 1 per unit. 13.8 kV is the rating of the generator, and when we talk about rating, we talk about the terminal voltage. That means 1 per unit voltage means it is 13.8 kV. All right. 100 MVA is the power rating of the generator, and it is loaded up to 75 MVA now at zero point 0.9 power factor lagging. Okay, that means 1 per unit power will be 100 MVA, so 0.75 per unit is the power delivered now, MVA, and active power will be zero point 0.9 power factor lagging. Okay, so we can calculate the active power from here. Calculate the active power and reactive power if the minimum acceleration EMF is increased by 10%. Okay, determine the also the minimum if the excitation is rather EMF increased by 10%, and minimum determine also the minimum acceleration EMF expressed as percentage of the initial value below which the machine would fall out of step. So from the first part, you have to do for a change in field current, you have to change the calculate the change in active power. Obviously, this will be zero, no change in active power. And how much is the change in reactive power? From the previous example, perhaps you can do this. What you have to do here is that you have to calculate the minimum excitation EMF expressed as a percentage of initial value. Limit of under excitation you have to calculate. What determines the limit of under excitation? It is delta equal to 90 degree. So for delta corresponding to 90 degree, you calculate how much is the value of EF. And EF and field current, they are proportional. So from there, you can see what is the value of EF. That is the minimum permissible value of EF. Express that EF as a percentage of the EF calculated at the first part. That is the problem to be solved here. Its value of excess is given to be 40%, means zero point 0.4 per unit is the synchronous reactance, and mechanical input to be constant. There is no change in active power, so only there is change in field current. For change in field current, you have to calculate how much is the new value of EF, and this new value corresponding to delta equal to 90 degree will give you the minimum excitation voltage or minimum or limit of under excitation. Okay, so this is the problem. Perhaps you will be able to solve it. Any question from anybody? If you cannot solve it, or if you have still some doubt, you may ask me. So that will finish this content. So from next class, we shall be discussing about the frequency control. So we have discussed regarding the synchronous generator, because in this part we shall be discussing the control of frequency for which the generator is very much needed. Also, some discussion regarding the voltage control is to be made from our part, and that is how voltage may be controlled or reactive power may be controlled from generating station. That much we shall discuss. That's why we have discussed these issues corresponding to synchronous generators and also regarding synchronous motor. Okay. Any question from anybody? Bolo. If there is any question, you may ask. And if there is no question, I shall be calling your name. Abhijit Dash. Abhijit Dash.
Yes, sir.
Abu Soyed Sheikh.
Yes, sir.
Ogniva Chatterjee.
Yes, sir.
Amisha Parvin.
Present, sir.
Then Anushree Majumdar.
Present, sir.
Bishal Burman.
Yes, sir.
Chinmoy Kumar.
Present, sir.
Devanik Borua.
Yes, sir.
Gopal Medda.